So now that we've got the business stuff out of the way, we'll pick up where we are with regard to the Cretaceous-Paleogene mass extinction. And I need to put my remote in there. So as I talked about last time, I was ending up, I mentioned, there are a bunch of these alternative hypotheses that don't seem to be very good potential causal agents, but that there are 3 potential causal agents and major environmental changes that occur near the KPG boundary that are certainly worth investigating. And all of these have that most important aspect of a potential causal agent, and that is there is evidence of them independent of the extinction themselves. So we know all these 3 phenomena are real, they are at play at that time. And so we're going to explore them in this order, because that's the order in which they occurred. So we'll start with the Maastrichtian regression. So Maastrichtian, as I mentioned before, is the last age of the late Cretaceous epoch of the Cretaceous period of the Mesozoic era. And regression, in this context, it's a geological term. It means a lowering of sea level. In case you're wondering, the alternative is a transgression. The rise of sea level is called a transgression. So regressions and transgressions occur throughout Earth history. But the Maastrichtian regression is actually a pretty sizable one. And again, it's lowering sea level. I had, back in the day, that I used to have more essay-type questions on the exam. I had a student one year who talked about Maastrichtian regression was a time at the end of the Cretaceous where all the dinosaurs reverted to their more primitive state, and they became so savage that they all killed each other. It was amusing. Clearly, their wheels were spinning and they weren't getting anywhere, so at least they came up with something funny. No, it's not some sort of psychological regression. It's the lowering of sea level. So if you remember, when I talked about the geography and paleobiogeography of the Cretaceous before the second exam, I talked about how there was this shallow seaway that separated Laramidia on one side from Appalachia on the other side in North America. And it's not just that. All over the world, sea level is high for most of the late Cretaceous. But during the end of the Cretaceous, the sea level drops. So here it is right before the extinction event, and here it is at the boundary. And depending upon the particular geographic model, some people think that this interior seaway is coming from the north. A few people think it's coming from the south. This particular biogeographer uses it coming in from the north. And this is happening globally. It's not just a Western North American phenomenon. It is best understood in Western North America because we've got the best geographic maps there. It is easy to access those locations. But it's going on worldwide. And it has to do, among other things, with a change in the rate of seafloor spreading. So the activity of the mid-ocean ridges, which drive the surface expression of plate tectonics. When those mid-ocean ridges are really active, they swell up, they're basically hot and swollen. Well, the water that's in the ocean basin has to be splashed somewhere. It's got to go somewhere. It splashes up onto the continents. But when they slow down and they shrink, the water drains back into the sea. So just to compare, here is the Earth at about 90 million years ago, so early in the late Cretaceous. You can see shallow seaways separating many spots, subdividing many continents. And here we are at the boundary, and the seaways are reduced. There's more land exposed. Now, it's still actually a higher sea level than it is today, but much lower than it was before. Well, why would that matter? Why would these changes matter? Well, for one thing, it's going to change planetary climates. Because one big factor in generating a climate is what we call albedo, or reflectivity. And so it's changing the parts of the surface of the Earth that are absorbing heat versus reflecting heat. It's going to modify ocean circulation and ocean productivity. So we go from a world where there are these basins full of very warm water that are contributing to the global flow of water and nutrients, to one where we don't have those. And so the amount of algae in the sea, the amount of phytoplankton producing new food for the marine realm has gone away because there's a lot fewer shallow sea spots. Additionally, it crowds out the shallow marine community. So there's a basic aspect of ecology that the number of species a habitat can support has a relation. It's a nonlinear relation, but it is a positive relation with the area. So when that area gets reduced, the amount of biodiversity it can support goes down. Well, if it's going down everywhere, that means we're going to be losing large parts of the shallow marine community in terms of biodiversity. In terms of the terrestrial realm, the climates get more continental, by which I don't mean they get more sophisticated and they can speak about philosophy and art. No, I mean, it becomes more extreme. So, a continental climate is one where you have more intense winters, more intense summers. When you're near the sea, that ameliorates, it levels the conditions. So here, for instance, on the eastern seaboard, we get cold winters, we get hot summers, sure. But if you took our same latitude and went to the interior of the continents, their winters are vastly colder, and their summers are pretty darn hot. Maybe not as humid as we get, but really hot. And that's because the moderating effect of the ocean isn't there. Well, the world went from a place that was basically wall to wall, or pole to pole Jamaica. No place was really far away from the ocean except for the interior of Asia, to one where there were continental interiors, so you get more extreme conditions. Also, when you change the climate, you're changing the habitats and the growing season and the plants that are supported, so you're modifying the base of the food chain. Well, if this is the driver of the KPG mass extinction, our expectation would be that the transformations of the biosphere would occur over the millions of year time frame. Because this was a phenomenon that took millions of years to happen. So, these are snapshots of about 1 million years apart along the top there. Okay, second major phenomenon, the Deccan Traps. And I'll switch over in a moment to show a background where you can see the text better. But the stuff in green on the map of India there, that is the current expression of the Deccan Traps. So these are a huge flood basalt event in western India. Remember, flood basalts are these extremely voluminous, lots of material erupted volcanic episodes. We've seen 2 of them before. The 2 we saw before was in the boundary of the Triassic and the Jurassic, the CAMP, the CAMP, Central Atlantic Magmatic Province. And the even bigger one before that, at the end of the Permian, the Siberian Traps. Note that those 2 events are also mass extinctions. And the Deccan Traps is the largest eruption, or perhaps one of the largest eruptions, that the world had seen since those 2 events. Individual layers of lava up to 150 meters thick, something like 2 million cubic kilometers erupted. And as I mentioned with the Siberian Traps, traps doesn't mean you're stuck in them. It's not that kind of traps. It means stair step. And I think you could see, or step. You could see the way this eroded here, how it looks step-like. Now, the Deccan Traps don't erupt exactly at the boundary. They erupt more than 250,000 years, but not that much more than 250,000 years before the boundary. Somewhere between 500,000 and 250,000 years before the boundary event. We know that because we can date these. First of all, they're igneous rocks, so we can get radiometric dates. Second of all, we can use geomagnetic markers. Remember, I talked about it, we can use a flip-flop of the polarity of the Earth's magnetic field. And that's preservable in some iron-rich sedimentary, but also certain igneous rocks. So we can get those here. And we can see that in the layers in between the lava, when life would recolonize that part of India, we still have, in the lower levels, titanosaurs and Mesozoic mammals and troodonts and so forth. And then above, after a certain while, we stop having those. So here's a typical day in western India in the end of the Cretaceous. So this map shows some of the extent. The olive color represents the preserved part of the Deccan Traps. And another photograph of how these huge deposits erode in the modern world. So the expected effects of Deccan Traps volcanism would basically be just like the Permo-Triassic or the Triassic-Jurassic event on a smaller scale. So global warming due to lots of CO2, perhaps a pulse of cold at the beginning due to sulfates. Now, being a massive outpouring of greenhouse gases, we might expect it to look relatively instantaneous in the rock record, particularly if we don't have a high rate of sedimentation in the area we're looking. So something that occurs over the space of a few hundreds of thousands of years is sometimes hard to tell from something that happened instantaneously. However, there are some spots in the world where we might get enough rapid sedimentation that we could expect to see the effects of Deccan volcanism over time. Here's just showing the a recent paper showing a huge pulse. So Maastrichtian over here, Damian over here. A huge pulse of this volcanism shortly before the boundary. There actually is another pulse that occurs somewhat afterwards, and a slightly smaller one after that. But we see the intense one right here. So shortly before the impact, shortly before the boundary, we'll get to the impact in a moment. And note that this transformation occurs during a what's called magnetic reverse period, but the earliest stages, the very lowest levels of the Deccan Traps volcanism actually began down here in a magnetic normal, so when the magnetic field is the same as it is today. So it was an extended event, even though there is a strong pulse shortly before the extinction. Now, it turns out in the American West, it has actually a pretty good record. It is, in fact, as we'll see, it is the best record we have of the end of the Age of Dinosaurs in the terrestrial realm. We have lots of thick deposits of sediment, and it turns out we can actually see the impact of global warming from the Deccan Traps volcanism reflected in the climates of Western North America at the same time. So in red, we see a way of estimating mean annual temperature based on the leaf formation, the leaf morphology, the shapes of leaves that are found in lake deposits. And we see that the average temperature, in this case of North Dakota, in the lower part of what's called the Hell Creek Formation, so this is the formation with Triceratops and Tyrannosaurus and Ankylosaurus, it's starting somewhere around about, 10 to 12 degrees centigrade as the mean annual temperature. So it's not tropical. Don't get the idea that Tyrannosaurus is running around in the tropics. This is not that much warmer than it would be today. But in the later part of the Hell Creek, after Deccan Traps volcanism has started to go, the temperature bumps up by several degrees. So here it is around 16 or so. So it's jumped. In fact, it's jumped comparable to some of the business as usual models in terms of global warming that we're facing. And so that seems to be the effect of the Deccan Traps warming for at least the initial pulses of the lava. And as I talked about before, we have other mass extinction events that are associated with big flood basalt eruptions. So there's a KPG with the Deccan Traps, but the Triassic-Jurassic event coincides with CAMP, the Central Atlantic Magmatic Province, and of course the biggest mass extinction of all, the Permo-Triassic event, is associated with the Siberian Traps. So we can't just immediately dismiss the Deccan Traps. We have to consider it seriously. But there is something else that goes on with the KPG boundary that we don't see at typical mass extinction events. And its discovery is one of the great examples of sort of pure science, non-applied science that we've ever seen play out in the history, especially of the earth sciences. Now, there are some spots of the world where we actually have a relatively continuous record of sedimentary rocks from the end of the Cretaceous into the beginning of the Cenozoic. Sometimes, like in North America, Western North America, it's in the terrestrial realm. But some places, like at this spot in Gubbio, Italy, in Tuscany, it's in the marine realm. It's limestone, so typical shallow water sediments produced in warm, shallow water. But it turns out there's an interesting outcrop in this place in Gubbio that people have since seen elsewhere, where we've got Cretaceous sediments, Cretaceous limestones, we've got Paleogene limestones, but a very thin layer of clay, so not limestone, but detrital sedimentary rock between the two. You can see how thin that layer is. It's eroded back, it's a tiny little thing, and in the late 1970s, it's at the boundary, in the late 1970s, the guy on the right here, Walter Alvarez, a geologist at UC Berkeley, wanted to answer a question. And it's a question involving, and his fingers are on that boundary. And it was not what caused the end of the dinosaurs. That's not the question he wanted to answer. He wanted to answer a far more simple question. How much time is represented by that clay? It's a really abstract, pure science question. How much time is represented by that clay? And it was an interesting puzzle because you couldn't answer it using typical methods. First of all these rocks are sedimentary rocks. There aren't ash beds in here, so you can't use radiometric dating. Secondly, you couldn't use magnetic stratigraphy. First of all, these are the wrong type of rocks to record magnetism. And secondly, there is no flip-flop right around the boundary. There's that sort of bracket I showed on the figure before that goes for about 1 million years or more. So that's not going to help. You can't use biostratigraphy because, first of all, the clay layer doesn't have any fossils in it. And secondly, the rocks down here have the index fossils of the very latest Cretaceous. And the ones up here have the index fossils of the very earliest Cenozoic. So how could you figure out how to answer that question? Well, like many people who are puzzled on a problem, he went to his dad for help. Now, it helps when your dad is a Nobel Prize-winning physicist. So Louis Alvarez, Nobel Prize-winning physicist, he had been involved with the Manhattan Project, so the project to build the first atomic bomb in World War II. In the post-war era, first Louis was involved in weapons design and discovering the intensity of the atomic weapons. And so a lot of that involved, comparing the yield, that is the destructive power of the atomic weapons with the size of the craters they formed. That actually got him to the attention of NASA as astronomers were intensely exploring the moon on the way up to the Apollo project, the landing on the moon. They wanted to study the cratering on the moon and figure out what were the size of the objects that produced those craters, because the craters there were produced by impacts of asteroids, of objects falling out of the sky and blasting out these craters. And so he could do the math to figure out how big an object would produce what size crater given the parameters of the gravity of the moon and the speed asteroids travel and so forth. So a smart guy, Nobel Prize winner. So the two of them said, okay, let's try a different approach. There's material falling into the Earth's atmosphere all the time because of meteorites. So little bits of space junk hit the Earth's atmosphere, they burn up. And some of that material will settle down onto the surface of the land and onto the seafloor and accumulate. So what we need is a type of material that's coming into the Earth's atmosphere that wouldn't be there except from space, or at least we wouldn't expect it to be there except from space. That's not really chemically active, so we don't expect it to be removed by chemical processes or added by chemical processes, and which is detectable. And they said, we have no idea what it should be. Let's go talk to some chemists. So they talked with a couple more chemists, just went across campus, talked to some chemists, and came up with a plan, and that's to look at iridium. Iridium is a platinum group metal. In fact, it looks, if you have a chunk of iridium, it looks like a chunk of platinum, which is to say it looks like silver. It is not a particularly reactive material. It is far more common in space rocks and meteorites than it is on the Earth's surface. It's pretty darn rare on Earth. And so that we have sort of a background rate, a flux that we can measure in the modern world of the rate of incoming amount of iridium over time. So they said, great, we can sample the rocks below, at, and above the clay layer, measure the amount of iridium, divide the amount of iridium we measure by the average rate of infall, the average flux, and that'll give us an estimate in years of how long that clay layer should be. They went through that, they measured it, and they said, wait a minute. Our data seem to be off. Except the data aren't off. The data are the data. The measurements are the measurements. What they saw was so much iridium in that little clay layer that it would have to have taken millions upon millions of years to accumulate at normal background levels. But they had the biostratigraphy to show that it wasn't millions of years missing. They had latest Cretaceous marine index fossils below and earliest Cenozoic fossils above. If there were millions of years missing, they should be having those particular index fossils. There would be other ones from further apart. So they said the flaw isn't the data, the flaw was the assumption of the average rate of infall. Maybe what we're looking at is a non-average rate of infall, like a greatly increased amount of infall. Like, oh crap. Maybe a really huge amount being introduced to the Earth's atmosphere all at once, like an asteroid hitting. So, how big would you have to have an asteroid if we're going to increase the amount of iridium that much? Calculate, calculate, calculate. Something on the order of 10 to 15 kilometers across. So the diameter of Manhattan Island or Mount Everest. Oh crap, what happens if something that big hits the Earth at cosmic speeds? Too bad we don't have anyone on our team who's used to calculating. Oh wait, we do, Louis. So they talked to Louis Alvarez, they did the calculation, and they said, I think we have what caused the Cretaceous tertiary extinction. Now, note that iridium there's nothing nasty particularly about iridium. It's not a poison. That's not what they were looking for. They used iridium simply as a marker for average rate of incoming material to figure out what's coming in. As it turned out, they picked a lucky thing because it showed them the possibility of something really dramatic. An object 10 to 15 kilometers in diameter hitting the Earth at the very end of the Cretaceous. But this is one site. Maybe there's something peculiar with the geochemistry. You need more data. And they did. They went around the world. They looked at terrestrial deposits. They looked at marine deposits. They looked at deep sea cores. And spot after spot after spot showed an iridium spike. The spike is so called because of the increase of abundance. It's still tiny, tiny amounts. You still need sensitive machines to find it. But the amount goes up by many orders of magnitude. So they said this is probably due to the infalling of an asteroid. So what's an asteroid? Asteroids are bits of protoplanets that broke apart early in Earth history. Many of them are concentrated in certain parts of the solar system. So here's the main asteroid belt. And here are some other concentrations. There's other clouds elsewhere. And those of you who watch or read The Expanse know that the belters, they suffer a lot out there. Those who don't know what I'm talking about, go watch it. It's a great series. That final season is going to be airing at the end of this week. So, okay. So, asteroids, big chunks of space debris, protoplanets that broke apart. This gives us a sense of the size of them. So over here, these are some comets looking with a 1 kilometer diameter, and over on the other side are asteroids, and you see a 10 kilometer diameter. And notice some of these objects, like Gaspra or Deimos, Phobos and Deimos, the moons of Mars, are really just captured asteroids. So things like Gaspra or Deimos are right about the same size as the object that was interpreted to hit the Earth. And so here's a sense of an object like this hitting the Earth and going boom. Now, when they proposed this in 1980, 79 and 80, they didn't know where the impact site was. And there was a very good chance that it wasn't going to be recoverable. After all, plate tectonics chews up ancient seafloor. So first of all, most of the planet is ocean basin rather than continents, so better chance of it hitting an ocean basin than continental rock. And if it hit the ocean basin, there's a chance that it had been chewed up and plunged back into the deep sea, or rather into the mantle, since in the last 66 million years. But that didn't mean they weren't going to look. And in fact, lots of people got in on this. So first of all, they said, even though we don't know what the asteroid site was, we can make some estimates. First of all, the idea is that it's an object on the scale of 10 to 15 kilometers in diameter. Back-of-the-envelope calculations, or actually a little more sophisticated than that, suggest that this solar-sized impact is something on the order of 1.8 times 10 to the 8 megatons. Now, a megaton is the explosive power of 1 million tons of TNT. And 10 to the 8 megatons is something like 1,000 to 10,000 times the explosive power of the nuclear arsenals of the entire planet at the height of the Cold War. So this is like 1,000 to 10,000 World War IIIs fought at the same moment. Or about a century's worth of the annual output of geothermal energy. And so they predicted that such a blast would throw huge amounts of material high into the atmosphere. Some of that would rain down right away. The material would go on ballistic paths and fall back into the atmosphere. Others would stay up in the stratosphere for long periods of time, and both of those would have devastating effects. But in particular, the thing that the Alvarez team focused on was the stuff that stayed up in the atmosphere, because that would block out incoming sunlight and plunge the world into darkness, and therefore take out the base of the food chain. It's what became called impact winter. And the idea there was an analogy to nuclear winter, which was also being recognized at the time as a potential effect of a nuclear war. Even a limited nuclear war would throw up lots of debris into the atmosphere, burning soot from cities on fire that couldn't be put out, which would potentially cool the world into a winter state in the aftermath of a nuclear war. And so here we have, some triceratops looking in the wrong direction as the asteroid goes boom. And then in the days afterwards. Now, the asteroid hypothesis really got the attention of, well, basically everyone, not just scientists, but the general public, because let's face it, this is a super dramatic potential mass extinction causal agent. And so animators and documentary makers and so forth just love it. And artists and so forth. So, and there's the idea of the crater. We would expect a crater somewhere between about 120 and 200 kilometers in diameter to be generated by this. And it was eventually discovered. It was discovered about 10 years after that first paper came out. It's called Chicxulub crater, so called after one of the towns within the crater. It's a Nahuatl word, so the language of the Maya. It's in the Yucatán Peninsula of Mexico, so not terribly far from places like Cancun and so forth. You can't drive down there and see it. First of all, it's too big. It's about 180 kilometers in diameter. That's too big an object to perceive. Also, it's buried. There's depending upon where you are, 300 meters to a kilometer of later rock deposited on top of it. So you can't go out there and see it. It's not a meteor crater in Arizona. But it's right there, right at the KPG boundary. It was discovered initially by drilling, by boreholes that were done by petroleum explorers in Mexico. And they noticed this huge disrupted layer right at the Cretaceous Paleogene boundary, Cretaceous Tertiary at the time. They thought it was something volcanic, but it looked weird even as a volcanic idea. Broken material, molten material that had chilled, all sorts of weird stuff. And it's after people started looking for a potential crater that they went back to look at these cores and said, wait, this might be it. So they decided to look for other evidence. Well, I'll skip to this one below first. They looked at gravity signals. There's slight differences in gravity depending on the density of material below, and looking at that, doing gravity scans of this region, look, this bullseye symbol. And there's the town of Chicxulub right there. They looked at magnetism, the melting and reheating, the melting and cooling of the material can leave a magnetic signature in molten rocks, and they saw something similar. Seismic detectors, sort of see below the ground, showed this bullseye shape there. But there's also a pattern that was already visible on the map, but this explained it, something they hadn't seen before. That's just the Chicxulub crater. If you just looked at it, one moment. Yeah, I'll talk about the sinkholes in a moment. But was that another question?
I was going to ask on the graph, the previous slide, what are the white dots?
The white dots, those are cenotes. Those are the sinkholes. We'll get to them in a moment. I have another slide with them on it. So you can quote unquote see the crater if you can use radar and you look at it from orbit. So this area is covered with trees and other stuff out there. You know, it's Cancun, so it's the Yucatán, so it's jungly. But you can see this area, which is slightly more level, and then these darker things, and those are some of the white dots that were there before. Oops, wrong way. Oh, there they are. These dots are called cenotes, and what they are sinkholes. A cenote, that's a local word for a sinkhole, is a spot where the limestone, that's the bedrock, gets eroded away by action of groundwater, and it leaves these pits in the ground. Now, cenotes have historically been extremely important to the people of this part of Mesoamerica because they fill in with water. You know, there's a lot of rain down there. So these are actually major sources of fresh water for the peoples that have lived in the Yucatan, since the humans first arrived there. And it turns out some of these cenotes trace out a circle, or at least a half circle. There's other ones distributed elsewhere, but these ones trace out a half circle. And it turns out the reason they do that is the fractured bedrock below, the fractured crust below, preferentially causes drainage of groundwater above it. And that continuous drainage of groundwater eats away at the carbonate rocks that are there. Whereas in other parts, it's more randomly distributed along the fracture line of the edge of the crater. You get a trace. So that was actually pretty cool. And again. But of course, before the Chicxulub crater was discovered, people were looking for additional lines of evidence, particularly because it was such an extreme idea, such a literally outworldly idea. People said, in science, it's not the most dramatic idea, that's what we use, it's the one that's best supported by the evidence. Let's see if there's other evidence for it. And a lot of people were trying to look and not find it. They didn't want this hypothesis to be true, and nevertheless, they kept on finding evidence for it. One good line of evidence is what's called shocked quartz. So quartz, super common mineral, one of the most common minerals on the surface of the crust of the planet, and also one of the most durable. And it turns out that a quartz grain, a quartz crystal, that's been subjected to high pressure will fracture, fracture planes in them. Now, volcanoes can produce shocked quartz, but typically there's only one set of fracture planes that form in them. However, nuclear blasts and places where we knew there were asteroid impacts already, something about the nature of the shock waves produced by them produce multiple planes of fracture within the quartz crystals. And so these are microscopic views using different sorts of lights. This is normal light, polarized light, looking at quartz grains. You can see this multiple planes of shock planes, multiple directions of shock planes in this quartz crystal here. You can see a sense of that down here, a set going that way, a set going that way, a set going that way. And these turned out to be pretty common in KPG boundary spots in the Western Hemisphere. And so here's some shocked quartz. There were other proxies, other lines of evidence of the impact. people found what they called tektites, or melt blasts. Tektites are commonly associated with meteoritic impacts. What they represent is material that's been blasted out of the ground, that went up high into the atmosphere, or outside the atmosphere, and re-entered. And as you know, the stuff re-entering melts on the way down, or heats up. In this case, it melts. It goes to a molten state. When it gets to the lower levels of the atmosphere, it chills. It doesn't have time to crystallize, so it forms a glass rather than a crystal. And here we see a bunch of spherules, of spheroidal tektites from the boundary. Also, there are places where we see ejecta sediments. What's that? That's material that's been picked up and flipped over and thrown out sideways. If you ever do get to places like the meteor crater in Arizona, there are blankets of these ejecta sediments that are shed all over the place around that event. And tsunami deposits. So deposits generated by tidal waves. And in fact, you can look at the paleo depth, how far down in the water column the disturbed layer was, and that tells you the intensity of the tsunami that was there before. The stronger the wave, the further down in the water column it disrupts. And it turns out all these events, this is showing how we can look at the paleodepthymetry there, of the depth of the tsunami there, about almost 500 meters down. When we go around the world and look at the intensity of these materials, you see, first of all, that many of these things, like the ejecta deposits, they tend to be concentrated in the Western Hemisphere. In fact, they tend to be most common in Northern South America, Central America, North America, and the Caribbean. Not a surprise. They all form sort of a bullseye around the Yucatan. And if you look at the thickness of the sediments that are destructed, they're tens of meters thick in these spots in purple. They're meters thick in the spots in red. They're centimeters thick in these other spots in orange. And in the rest of the world, it's millimeters thick. So that really does form sort of a bullseye towards a blast in the Yucatan. Incidentally, there have been people who have proposed that there was a second impact, for instance, maybe in the Indian Ocean. But if there were, where's the traces of it? We would expect this intense bullseye effect over there, but we don't see it. So here, for instance, is a spot in North Dakota, courtesy of my colleague, Antoine Barkovici, a guy who works on pollen at this time. So down here, we see what's called the boundary clay. So this is material, this actually represents ash that's come down. We have the spherules above that, the little droplets, the tektites. We actually get the shocked quartz and the iridium above that. But these are just, we're talking just a few centimeters over here. And then typical latest Maastrichtian sediments up there, and typical earliest Danian, earliest Cenozoic material above that. So, some people thought maybe the Chicxulub Impact, it's on one side of the world. Deccan Traps, it's on the opposite side of the world. Maybe the Chicxulub Impact caused the Deccan Traps volcanism. Maybe a shock wave passed through the world and caused this huge burst of volcanism. There is precedent for that in other parts of the solar system. On the planet Mercury, there is a huge, gigantic impact on one side of it and a gigantic volcanic field on the opposite side of the planet. It's thought that maybe this was antipodal volcanism. However, it doesn't work here. As I mentioned before, we know the Deccan Traps volcanism. Well, first of all, we know the impact occurs during a reversed magnetic time, what's called C29R. So the R's are reversed. But Deccan Traps volcanism starts during a magnetic normal interval, which is at least 250,000 years beforehand. And it turns out with the radiometric dating, it's even older than that for the Deccan Traps. Not much, but older. So the Deccan Traps volcanism was already going It was already a thing in play. That said, it wouldn't be surprising if that later pulse, when I showed the pulses before, the later pulse of volcanism from the Deccan Traps, which is thousands of years after the impact, might have actually been caused by the impact, because it might take that long for the big blob of magma to work its way up. Because indeed the world would have been really shaken. Now, unlike all the other great mass extinctions, all the other big five mass extinctions, which seem to have had a trigger that occurred over the course of thousands of years, or tens of thousands of years, the KPG is Earth's worst day ever. It was a singular day. We'll talk and so on Wednesday that Deccan Traps and Maastrichtian Regression have a role to play, but it's this really intensely horrible day that is the primary cause based on most of the evidence. And it happened in phases. Even though the phenomenon occurred in just the course of a day, it played out over a long time. The first phase is the shockwave and tsunami. This is the part that Hollywood loves. So the impact generates at least a magnitude 10.1 earthquake. I've seen some estimates of a magnitude 12. Even a magnitude 10.1, if it occurred today, would knock every building in the world down, essentially, regardless of where the earthquake occurred. Some buildings might just be lucky enough or a stable enough base to survive, but it would have potential to knock buildings down everywhere. This is more intense than any earthquake in human history, thank goodness. So you get this shock wave coming out, where the blast occurred, this huge blast coming out, and also a thermal pulse, when suddenly you convert lots and lots and lots of potential energy into kinetic energy into radiant light. So this pterosaur here, the question is going to be, will the shock wave get to it first, or will the thermal pulse come out and obliterate it into, it's lighted on fire, and then as it's falling down out of the sky, it gets hit by a shock wave and turns into ash and dust. And a tsunami that spreads out around the world, which, depending upon where it hits, is between 100 or 250 meters high. So, huge, huge devastation. But you know what? This is destructive. This is not a mass extinction-inducing thing. Regionally, it would have been devastating. It would cause some extinctions around the world, but this would not rise to the level of the Big Five. But the subsequent effects are what are the major killing agents. Phase 2, so we've got this blast wave coming out, radiating around the world. Phase 2, you also have all that material that was thrown high in the atmosphere, and now it's beginning to rain down all over the world on these ballistic paths. It's what I call the easy bake oven. Now, I don't know if they still make these. Easy bake ovens are these toy ovens that they could give to kids. And the way they work is you've got a heat lamp in them, and so it doesn't actually get as hot as a normal oven you would have in the kitchen. If they did, they wouldn't let kids play with it. Instead, what happens is you put your brownie batter in there, and the brownie batter is opaque, and it absorbs most of the heat coming from that heat light, although the air itself doesn't get as hot as an oven would. Well, in this case, we have all this material collapsing back into the Earth's atmosphere, falling out of the skies, everywhere. And indeed, the physicists estimate that you would feel an infrared pulse, a heat pulse, equivalent to 8 to 10 times the heat you feel at noon at the equator today, everywhere. So everything is getting hit by heat. The air itself only rises up by about 10 degrees C, 18 degrees Fahrenheit. But non-transparent objects, like flesh and leaf, are taking this full heat load. And so they're baking, they're cooking. And cooking is physiologically not a favorable thing for living tissue. Now, life in the soil would be protected at depths up to about over 10 centimeters. And things, at 9 centimeters, it wasn't like they're going to all die. They'd have some protection. At 8 centimeters, it's all protection. Even at 1 centimeter, they'll have some protection from this heat. Life in the water is perfectly protected, because all this thermal energy is hitting the top layer of water, it's boiling off like a micron or two. You stick your snout up, you take a breath, the air's hot, you singe your nose, but you can go back in the water. But terrestrial organisms are going to bake, and the estimates range from several minutes to possibly hours. And this might explain an important factor here, which is that all larger land animals, all animals about 5 kilograms or more, die out at this event, because they can't hide. There's no place for them to go. But there's more to come, and in fact, there's even more in phase 2 to talk about. We'll pick up next time. Maybe wishing on a shooting star wasn't the best move there. So we'll pick up next time with the global forest collapse and the rest of phase 2, and then move on to phase 3 and phase 4.